Now I would like to derive the green function again, but this time by using the Fourier transform. Here we use the Fourier transform between space and wave number. The target equation is the following green function problem. First, let us recall the Fourier transform pair. A spatial function can be transformed into its wave number spectrum, and the original function can be recovered by the inverse transform. Next, we need one important property. What happens when we Fourier transform a spatial derivative? If we Fourier transform the derivative of f with respect to x and integrate by parts once, we obtain the following equation. Here, the function vanishes at plus and minus infinity, so the first term vanishes, and the second term is equal to f of k sub x multiplied by minus jk sub x. Therefore, for the second derivative, we simply obtain minus jk sub x squared, that is minus k sub x squared, acting on the transformed function. Now let us apply this to the green function equation. The second derivative term becomes minus k sub x squared in the Fourier domain. The k squared term remains as it is. On the right-hand side, we need the Fourier transform of the delta function. By the property of the delta function, this gives exponential of jk sub xx prime. So the green function in the wave number domain is obtained immediately by simple division. This is one advantage of the Fourier transform. Instead of solving a differential equation, we only take algebraic operations. Therefore, by taking the inverse Fourier transform, we can obtain the green function in the space domain. Here we write the denominator in this form so that the poles can be seen more clearly. The integration path of the inverse Fourier transform runs along the real axis from minus infinity to plus infinity. To evaluate it, we extend the integration variable k sub x to the complex plane and treat it as a contour integral there. To determine how the contour should pass these poles, we consider a medium with a very small loss. Then the conductivity is not exactly zero and the permittivity becomes complex. As a result, k also becomes complex with a negative imaginary part. In the lossless limit, we interpret this as an infinitesimally small negative imaginary part. This tells us how the poles approach the real axis and therefore how the contour should avoid them. Now let us evaluate the inverse transform. If x minus x prime is positive, we choose the contour in the lower half plane, so that the exponential factor decays. Then the enclosed pole is k sub x equals k. If x minus x prime is negative, we instead choose the contour in the upper half plane. Then the enclosed pole is k sub x equals minus k. Evaluating the residues, we obtain the green function in exactly the same form as before. So even though the method is different, we recover exactly the same green function. This shows that we can derive the one-dimensional green function in two equivalent ways, by solving the differential equation directly or by using the Fourier transform and contour integration.